Hello everyone, my name is Ajay Medji from Aeronautical Engineering. In this presentation, I am going to discuss about my concept video of aircraft structures. My concept video topic is characteristics of composite materials. Before going to discuss about characteristics of composite materials, now we will see what is meant by composite material. What is composite material? A composite material, also called a composition material or shortened to composite, which is common name, is a material which is produced from two or more constituent materials. These constituent materials have notably dissimilar chemical or physical properties and are merged to create a material with properties unlike the individual elements. Within the finished surface, the individual elements remain separate and distinct, distinguishing composites from mixtures and solid solutions. The most appropriate properties of composite materials are high stiffness and strength across a wide range temperature, high Young's modulus, high resistive to corrosion oxidation, low density and lightweight, high thermal and electrical conductivity, high wear resistance. Let we see that the characteristics of composite materials. There are many types. In this video we will discuss some important characteristics. The first one is mass. Carbon composites are generally considered 4 times lighter than most steels. Density of steel is 7.8 kg per meter cube. Density of graphite damping composite is between 1.4 and 1.8 depending on composition. It has good damping. Damping is up to 20x better than steel when damping material is included in the composite. The inclusion of damping material will reduce composite E modulus. The resulting composite E modulus is still similar to standard steels. The positioning of damping material in the component is an important element of the design process. Second one is stiffness. E modulus of a graphite layer in the direction of a fiber can be over 400 gigapascal using 760 gigapascal fiber. A quasi-isotropic steel equivalent complete laminate will be an E modulus of 150 gigapascal in both x and y directions. Hence, the need to use 1.3 times the thickness to maintain the equivalency of 210 gigapascal steel. Optimizing the stiffness in different directions or between bending and shear stiffness is a normal part of the design process, which is not possible with steel. And the third most important characteristics of composite materials is strength. The maximum strength of a steel equivalent composite is about the same as the yield point of standard steel, about 385 megapascal. Many machine components need stiffness or damping rather than strength, and the volumes of material necessary mean that the steel levels are consequently very low. Here we can see the graph between tensile stresses to equivalent stresses. Now we will see about failure. Composites do not have a yield point. Composites could micro crack in the matrix at about 75% of ultimate load. This can be considered to be the composite equivalent of a yield point. However, unlike steel, the E modulus does not change and the stress strain curve is straight line until failure. The maximum strength of a steel equivalent composite is about the same as the yield point of standard steel at about 385 megapascal. Many machine components need stiffness or damping rather than strength, and the volume of material necessary mean that the stress levels are consequently very low. Failure. Composites do not have a yield point. Composites could micro crack in the matrix at about 75% of ultimate load. This can be considered to be the composite equivalent of a yield point. However, unlike steel, the E modulus does not change and the stress strain curve is a straight line until failure. Composites fail in compression or the compression side of bending at about half the tension failure stresses level. Fatigue. The SN curve for carbon fiber composites is very flat and significantly better than steel. Expansion. PAN fiber has a positive coefficient of thermal expansion. Graphite fiber has a negative coefficient of thermal expansion. When made into a composite, it can be designed to have a zero expansion in a specified direction, provided this does not conflict with other required properties. Machining and precision. In composites, it is not good to cut the fibers that are responsible for stiffness or strength. It is usually to add an extra layer of some material in order to create machined surface. Carbon composites machine well, but require special equipment for the safe disposal of dust or slurry. Accuracy of tooling dictates the accuracy of part, and this is very useful in obtaining accurate inside dimensions without machining. This can be a significant saving. Eighth one, stability and drift. Experimental measurements show that for precise positioning of a beam, the Composite composite is better than pre-preg composite. The pre-reg beam would drive over micro time and loses its positional stability. The reasons are that residual stresses are built into the pre-preg beam during curing. The Composite production process does not have this problem, and the Composite beams pass the criteria for stability. In this diagram, it is showing the drift comparison and equivalent stress. You can see ninth one, environmental. Corrosion. Expo composites do not corrode fluids. Epoxy resins are impervious to fluids, and a good composite has very low voids. However, if the composite is machined, the surface of both the resin, any filler and the fibers may be cut. Anywhere that is machined needs to be recoated to ensure a good seal. Temperature. The epoxy resin matrix is chosen partly for its temperature performance. Anywhere in the range -40 degrees to +200 degrees is normal. Higher temperature may be possible. Ultraviolet light. UV is a problem for epixo resins, and there are many additives to reduce this degradation. However, this is only a surface problem and can be overcome with the correct choice of coating should there be any danger of UV. Healthy and safety. Once a composite is manufactured, the only health hazard is dust from the machining, grinding or sanding of it. This is overcome by the use of fluids or strong air suction to remove any particles. Recycling. Unwanted composite is chopped and the matrix burned off to recover the energy trapped in the chemistry. The short fibers are used for reinforcement in injection molding or concrete. Other possible recycling processes will convert the material back to basic elements. Applications of composite materials. Space, antenna, radar, satellite structures, solar reflectors, etc. In aircraft, airfoil surfaces, compressor blades, engine bay doors, fan blades, rotor shafts in helicopters, turbine blades, turbine shafts, wing box structure, etc. Automobiles. automobile body, bumper, mudguards, door panels, dashboard, drive shaft, fuel tank, CNG cylinder, chassis, fender, etc. In wind turbine blades, rotor blades, nose cone, nacelle lay cover, accessories for wind energy, wind electric energy generators, sports, skies, surfboards, windsurfing, table tennis boards, slats and gliding wing spar, tennis, badminton, fishing rods, golf clubs, baseball bats, hockey sticks, pole shaft, sword, etc. These are the applications of composite materials. Thank you.